All right, guys, we're back. We're going to look at this problem again. This is similar to the problem that you had in section 4.4 number 2, which the rectangle is inscribed in a circle of diameter 12. And there's a follow-up part to this problem in the later exercises. So here we're going to refresh your memory. Okay, this is the rectangle here. We actually end up showing you that the rectangle of greatest area is going to be when that's a square, but we didn't actually show you that analytically. So we want to go through that, and actually in this one it expresses the area and the perimeter. Okay. All right. So let's take a look at that, and we'll go to our example here to illustrate that here. So here I've got this back here again. Okay. So in terms of that, what we call, remember we call this point here xy. So that's xy. But remember, y is simply, if you solve this for y, then y is equal to the square root of 25 minus x squared. Yes? Okay? The dimensions of this rectangle was here, this was 2x, because this length was designated x, and by 2y. So the area, as you can see, was equal to 2x times 2y. We showed you that, okay? Which means 4xy. But there again, that's not a function because it's not, it's not exclusively in terms of x. So we can then enter this as our x value. So then we get the area as a function of x is equal to 4x times the square root of 25 minus x squared. Okay, now let's look at what are logical limitations on that value of x. Okay, so being x is BE. If A was driven all the way up here, we've got no area, in which case we got x equaling, as you can see here, next to essentially 0. Okay, then we can move all the way down here to where x is right there at on the axis, where x is 5, but there again, with that being the case, we have no area. So we have restrictions on x being between 0 and 5 seem to be the logical restrictions. Being between 0 and 5 seem to be the logical uh, restrictions. Okay, so we're going to come back and we're going to state those restrictions on the variable. X is going to be between 0 and 5. Okay, now this is not quadratic. Okay, and it's nowhere near quadratic. I'm not even going to try to entertain the fact that it is not quadratic. So I want to go now and look at, can we optimize that? Well, we can optimize that, but analytically we have to wait till the calculus. But we can use our calculator and get my calculator. Okay, so we'll do the same thing as we did before. Okay, we're going to key that function in. All right, we're going to key that function in, and for now, I'm going to come and turn that guy off. Okay, we're going to key that function in. Then we're going to look at the windows between 0 and 5 and see where we can find our maximum point. So the function 4x times the square root, so times the square root of 25 minus x squared. Okay, let's see what that looks like. All right, now, okay, again, we don't even know what this curve is going to look like, but we can let our calculator help us find that point where it maximizes out. So again, we're going to look at our table. Our table set is going to start at 0. We're going to go to auto. We'll increment it in units of half, 0.5. Okay, and that'll be fine. Then we'll look at our table, and our table will look between there and see where does it peak out. Okay, um, okay, so where does this begin to peak out? Let's look at our x values. Okay, all right, and we're, again, we were interested in the value of x, okay, where this thing, and our x values can run up to 5, we've reasoned, okay? And you seem like somewhere in there, okay, at 5 is 0, but see somewhere in there it peaks out. About 3.5 looks like maybe it peaks out. So we'll run our x values from 0 to 5 and our y values up to 50. So we're going to set our window to go from 0 to 5 on x, okay? And then we're going to max out there at about 50. Give ourselves some breathing room. We'll go to 55, maybe even 60. Okay, so that's how we gauge our window so we can see where that thing is going to peak out. So now we take a look at the graph. Here's the graph, okay? The graph has an obvious high point in that range, okay? And so F5 will find that high point for us. All right, let's find that high point. That's the maximum. All right, and there we go. Hone in up from the left side over to the right side. Okay, and I'm doing that somewhere. It looks like I kind of made an issue with that. Let's run that again. F5. Okay, the maximum. F5 maximum. Right. Okay. From the left side, which is the lower bound of that high point. All right. Over to the right side. Be in there. That's good enough right there. Okay. Let it hone in on it. Comes back, reports 353 with the area of 50. Okay. And if we look at that on our calculator, on our sketch pad, okay, we're trying to find that x value when this area is as large as possible, and we can see that the area is still on the increase. It gets to about 50, it's going to max out right there, 353. So that's what we found from our calculator, and that's what we found from Sketchpad, and they are consistent. And the only thing we have to remember is we can get the function. We can very much get the function, okay? But unless the function is quadratic or quasi-quadratic, we're not going to be able to analytically determine where it peaks out. But we can use our calculator. And we will, and I will expect you to use your calculator using all those skills. Okay, there you go.